It's my real pleasure to introduce Franco Vargas Payet, who is going to talk about renormalized volume and isoperimetric profiles.
Thank you, Pilinio, and thank you again to the organizers for putting this event together and for inviting me. I think it was 2008 the first time that I came as a student for the summer program here. You may have seen some of the classes. So it's very special to be back here and talk something about my research. I've been telling you today all the original works are based in the joint works I had with Celso Viana. Maybe something to mention is that sadly at a very young age, Celso passed away a few months ago, which, of course, it's sort of like, a little bit difficult, I will say, for the field, for the community mathematics here in South America, and, especially for his family and the ones we had the honor to call him a friend. Celso was someone that, really loved mathematics, really loved to go to people's talks and getting talking with them. A lot of the work I'll be talking today is because of that. We were both at the same program at the IAS, so like fresh out of grad school, we both excited about volumes. I did renormalized volume, he did isoperimetric profiles, and we used to spend a lot of time talking. A lot of this work comes from those conversations. So, okay. Let me tell you a little bit before I may forget this during my statement. A lot of times I'm going to be talking about convex compact hyperbolic three-manifolds. By that, I mean this is going to be a three-manifold with boundary, comes as a complete quotient of hyperbolic space. And I'm going to assume it has a copy of itself that is both convex and compact. So here in orange, and is almost the same picture as Martin did yesterday, except like I put one more genus, so it's technically a new example for you. So I'm going to be mostly thinking about this. And maybe just to give you one example, I'll mention the case when I could just take a quasi-function group where the metric can be written as follows, cosine square g sigma, where sigma is a hyperbolic surface whose hyperbolic metric here is given by g. So in this case, it looks more or less like this. And r equal to 0 corresponds to one totally geodesic sitting there at the center. Of course, you can do quasi-conformal deformation. Those are the quasi-function examples that may appear a little bit later. OK. Let me first maybe now tell you what an isoperimetric profile is. So this is just going to be a function, it's a geometric function. And basically what it's telling you is for any given volume, what is the least amount of perimeter you needed in order to bound such a volume. So that can be formalized quickly into I want the infimum of all the possible areas of the boundary when I'm considering regions here in M that are going to be compact. I'm going to assume they have a smooth boundary, just to keep things simple. And I'm going to assume that their volume, which I will denote by brackets, has to be equal to V, where again here V is some positive number. Okay, so this is how I define it. There is going to be one variation of this that is analytically convenient. It's more or less the same type of behavior. Again, I'm taking smallest perimeters. Now I'm going to consider domains, again, still in M compact. But now I'm going to ask them to contain a particular region. I'm going to tell you in a second what it is. And I want the volume between omega and omega 0 to be equal to V. So what omega 0 here is, this is what is called as the outermost minimal region. It's supposed to be a region so that all possible minimal surfaces, all possible critical points of area are going to be contained inside. So here in my picture, in this particular case of this type of hyperbolic manifolds, there is always on each end one minimal surface, which is the minimal surface that is the furthest into the end. Meaning this is the last minimal compact minimal surface I will see. There is none such type outside of this. And they have to be contained within the convex core. So this is the cartoon picture you should have in mind. And from the definitions, if I'm remembering how my infimums are supposed to be defined, you will see that, so I think I have to phrase it a like this. Right, because here I'm being more restrictive by asking them to contain the outermost region. Okay, maybe just some side here, quick examples to have in mind. To put this in context is, let's say when I do this for R2, round disks are the ones that realize solve the isoperimetric problem for any given volume. And in this case, the isoperimetric profile should be pi over root, 2v over pi square root. So that's just one example for you to, this is just solving the area and perimeter relationship. Maybe another example will be for H3. So here, I won't put it in a closed form other than telling you that the volume of the ball of radius r, which is the one that realizes it for its corresponding volume, this is going to be pi sinh of 2r minus 2r, where the perimeter of this is now given by 2 pi hyperbolic cosine of 2r. And the part I want to highlight here is that, in particular, volume will be always less than 1/2 the isoperimetric profile. And the quotient of area divided by volume goes to 2 as you send volume to infinity. Okay. So now you may ask, well, here I'm claiming that this is realized in some cases, and there is already a quite known theory how these things are realized. So I'll just here write the theorem. This is a compilation of works from a lot of people, go also the way back to Algren. So it's Algren, Chen Simon, Morgan, and Eichmar, and Metzger. So it's just a compilation of all these works that says the following. Here, something I didn't mention is because I have a domain here that is convex, a feature of hyperbolic geometry is that the geometry opens up exponentially, meaning when I travel distance r, I see the sizes of surfaces growing like an exponential function in r. So in particular, injectivity radius is bounded below by a constant away from 0. This has bounding geometry. And in such a case, for any positive v, there exists a region sigma, which of course depends on v, such that the boundary, which I will denote by sigma, is smooth. This is a compact region with a smooth boundary that realizes the isoperimetric profile of my manifold for the volume V. And in general, this region may not need to be connected, may not need to be unique. For instance, in the case of the balls, you know that the ball is the one that realizes, but you could have it in many different parts of your manifold. So at least we have this result for existence. But now that we have a result for existence, in particular because our region has to be the one that has the least perimeter for a given volume, that means that if I perturb the volume smoothly, if I perturb my region smoothly while preserving volume, I know that area cannot increase. So that gives me two conditions, one for the derivative of area will have to vanish, and the second derivative of area cannot be negative. So now because of that, how do you perturb the region preserving the volume enclosed up until first order is, well, you consider a very function with average 0. This is going to indicate how much am I moving each point in the normal. Then the derivative is going to be given by twice the integral of the mean curvature times f over the surface. This is just the arithmetic mean of the two principal curvatures that tell me how much my surface is curving against the ambient geometry. So this is the first derivative. This has to vanish. And then the second derivative, which, okay, I won't bother much in the computations, but just tell you what it is, which is given by this. This has to be greater than or equal than 0. So this condition needs to happen for, let's say, any smooth f satisfying these things. So from here, for instance, we can see that sigma needs to have a constant mean curvature. So this is a smooth constant mean curvature surface, because this function needs to be equal at every single point, even if sigma will be disconnected. Okay. So it tells me that at least the regions that realize in this are some nice geometric regions, but it's not telling me anything necessarily from the profile. The profile doesn't need to be a smooth function, but it's more or less smooth in the barrier sense, because I can play now the following game. So now let me imagine this is my omega region with the boundary sigma. And let me assume that here I define sigma t as taking the exponential of t times the normal for sigma. So I'm just moving here as my surface, sort of like a unit speed, a little bit above, a little bit below. And now whatever I do, I need to be at least as big as whatever is the corresponding profile, and I need to be exactly equal at this particular value I'm assuming. So this is how you talk about differentiability in the barrier sense, because I will have here my profile m function, maybe a very non-regular function. But now these variations here, what they create is a family, or is a smooth function defined only in a neighborhood that it needs to lie above my profile, and they need to coincide at this point. So that will give me conditions, or the derivative of g will give some conditions in the barrier sense for the derivatives of I. So now, again, here, because I'm using the function equal to 1, I know like, well, the derivative will be given by the mean curvature, which is given as a constant. So when you solve here, you have that the derivative, so this will be the derivative from the left is going to be less than 2 times the mean curvature, the derivative here from the right. And for the second order equation, you have that the profile square second derivative plus minus 2 the normal second, or the second fundamental form. This needs to be less than or equal than 0. Okay, so it might not be a smooth function, but it has these properties. Now, of course, this means that wherever the profile will be differentiable, then the derivative is given by the value of the mean curvature at that particular time. Let me say from now on, I will just assume that I is, let's say, C1, or at least differentiable. So I will have equality here. All of what I'm saying, you can reframe it in a correct way, but either saying derivative from the right or derivative from the left. Okay. So from this, a nice corollary that justifies why am I talking about the other profile is that the other profile is not decreasing. And the picture proof will be as follows. So let me assume that at some moment decreases. So I will have that then at some point my derivative will be negative, and I know that this is the value of my mean curvature. So this is going to imply that at that particular, for that particular value of volume, I'm going to have here a surface, so the boundary of the corresponding region here by sigma. The sign of the mean curvature is going to tell me it's going to be mean concave, meaning the mean curvature vector, the one that tells you in which direction you decrease area, is pointing out. So that's what that sign is giving me. As I mentioned here, your geometry expands exponentially fast, and you have a lot of convex surfaces out there, meaning those are surfaces where your mean curvature is pointing in. So I have here something very close out there with the curvature pointing inside. Right? That just comes from the convex compact condition. And now I can use this compact region and minimize area using these two surfaces as barriers. So when I try to do that, because here area is being minimized pointing inside and outside, I can do a minimization process, or it's very classical nowadays for this procedure. And now this will create here a minimal surface here in yellow in this region, but the outermost profile was supposed to be strictly inside. So if I will have that sign, then I will see a minimal surface in a region I was not supposed to see it. So this is a nice consequence, or that's a good reason why you want to modify the isoperimetric profile and consider it like this. Okay. Before moving maybe a little bit to renormalized volume, let me give you one definition of something that is useful. Oh, sorry, was there a question? Well, let me know at any point there's a question. But let me define for you Hawking mass. So this is just a functional of the isoperimetric profile, and it's given by, I will define it as root of the profile, 2 pi all the characteristic of the boundary plus the profile minus the derivative of the profile squared divided by 4 times the profile. Okay? So that's just a function. I'm just defining that function for you. This is a useful function a lot of times to analyze, especially for isoperimetric problems. Let me highlight maybe some of the differences, especially that enter on this theory. There is a lot that has been done when either your ambient or your surface have a positive curvature or positive Euler characteristic, because that's going to determine certain signs that you get to use at different times that create some inequalities out of that. So this situation is very different from that, because we definitely have a negative sign coming from the curvature, and we definitely have a negative sign coming from Euler characteristics. So we really had to come up with different types of inequalities to study these functionals. But anyway, it's still the right functional to study. And maybe I will just, without proof, give you a proposition that this profile is also non-decreasing. And I won't go on to the proof, but maybe you can believe that over here I gave you a bunch of inequalities on the derivative and the second derivative. And now, if you want to prove this is non-decreasing, you differentiate, you try to solve a sign, and this only depends on the jet of your profile up to order 2. So I'm just telling you that if you operate and do just a little bit of work, you can prove that. Okay, so that's what I need for isoperimetric profiles as for now. So now, thanks to Martin, renormalized volume has been introduced. So I will just remember, or recall some of the facts that will be useful for this type of object. And this goes, let me maybe go more or less like this. So I have here my manifold. Let's say here I have surface sigma, which I will also assume it to be convex. And now I'm going to look here at the surface. So this is my initial region. And now here I will look to all the points distance r from my convex domain. That's going to be my sigma r. And something that came up in Martin's talk is that when I look to the metric of this boundary surface up until distance r, this is more or less or grows like cosine square of r, meaning like e to the r times some constants. But the principal curvatures, the two curvatures that tell me how much this surface is bending, these ones are converging exponentially fast to 1. Okay, again, this is not, Martin was describing just like how when you do this, the geometry of this thing is solved in terms of the geometry of the initial one. If you replace that and you take large values of r, this is the asymptotic behavior you will see. So now, because of it, you realize from here, I could take, this is the same limit Martin mentioned, as r goes to infinity, I could take the limit over cosine square, hyperbolic cosine square gr. This is going to be a metric at infinity. So this is going to be a conformal representative of the conformal type you have here. And thanks to work of Epstein around the 80s, is that this is, between quotations, reversible. Meaning if now you give a metric at infinity, there is more or less this equidistant foliation you can write in a very explicit way that will have this behavior. So now because of it, I will define, again, we'll recall for you what W volume is. So this is M with respect to some metric at infinity. And now, what I would really like to do, I would really like to just compute volume. This is the renormalized way to thinking about it. I would like to compute the volume of my region omega r. Of course, this doesn't work. This blows up exponentially. So now what you do is you subtract something that blows up to the same rate. So that now you blow up maybe a bit slower, and then hopefully subtract a number. Well, this blows up exponentially. So something that blows up to the same order will be the integral of the half of the mean curvature. This blows up to the same rate. This is not exponential anymore in R. This is now linear in R. So now you can subtract a term that is linear again. And this is the linear term that appears on Martin's talk. So now it turns out that if you take a limit here in R, this will be a finite limit. And actually, this is a constant function in R. So you could just evaluate it at any point. So that's what W volume is. And then as Martin also mentioned yesterday, is that the renormalized volume of M is none other than taking the renormalized volume when you associate the hyperbolic metric at the conformal boundary that there exists a unique hyperbolic metric in that given conformal class. And again, this has very analytical properties that Martin covered yesterday. So maybe I will just quickly give you the example that when you take the renormalized volume of a function manifold, well, for a function manifold, you can take things so that sigma 0, or like my initial sigma, is just my total geodesic surface resting at the center. So in that case, well, that has empty interior, so volume is 0. It's totally geodesic, so the mean curvature completely vanishes. And we were evaluating this for r equal to 0. So in this case, every single term vanishes. And we have that value. And it can be, you may debate yourself, why do we go to the work of defining a volume if that volume is just giving you the answer of 0? And one of the justifications of today is telling you that this is really comparing some volumes at larger scales. And that's one of the main parts I'm trying to get to today. Again, a theorem. So this is Richman, Brock, and Bromberg, and also independently of myself. So I was saying the case where M is acylindrical or quasi-function, again, right, these are the quasi-conformal deformations of a function manifold. These are the ones where you don't have essential cylinders going between your boundary. These are the two conditions that Martin mentioned yesterday for you to have a model metric. There is a unique model metric where your convex core here in orange is not this pleated bracket surface, but it's an honest total geodesic surface appearing there. There is a unique structure as such. And in this particular case, the renormalized volume of M has to be always greater than or equal than the renormalized volume of that special hyperbolic metric in M, with equality if and only if M has to be the geodesic model. And that's something that will be useful. Okay. Let me now just going to try to connect renormalized volume to the isoperimetric profiles. For that, there is a nice important paper by Maceo-Paccar that says the following. Again, I'm always assuming I have objects such as this, and I think from now on, I will also throw acylindrical or this as my conditions. But I will say in such cases, there exists a compact set K such that n minus K has a, and let me phrase this carefully, monotone increasing to h equal to 1 CMC foliation. And what I mean by that is that I will have outside some compact set that particularly it may contain, likely containing the convex core. It's going to be a foliation by closed surfaces. As I exit the end, you see the mean curvature increasing. The mean curvature will be constant for every leaf. And moreover, they converge from below to 1. And this is so something that's going to be important is that this will be strictly monotone. So there is such a strictly monotone. And the part that is important for us is that this foliation is really just a very small perturbation for the equidistant foliation you use in renormalized volume. So that's not quite clear from this. It's a little bit clear. It's also in the paper of Maceo-Paccar. They weren't looking at renormalized volume at the time, but it's a consequence of how they approach. And by that, I mean as r goes to infinity, the boundary of omega r and the corresponding constant mean curvature leaf, they are getting closer and closer together to a rate you can quantify. So that is how, at least in one hand, we are connecting, or like we could connect renormalized volume to this constant mean curvature foliation. But if I want to connect it to isoperimetric profile, then I will need to know that this foliation, which is a good candidate for a solution for the isoperimetric problem, it needs to be a solution of the isoperimetric problem. So that's still something I need if I want to connect these two theories. For that, let me give you one useful proposition. So let's say lemma. This is a nice exercise that if I take this convex in M and omega r, these are all the points that are at distance from omega less than or equal than r. Then as r goes to infinity, the area of the boundary of omega r is less than twice the volume of omega r. And it's really a computation because this difference is a linear function in R that goes to minus infinity when you have it. Again, the importance here of this lemma is that these regions, they're outperforming geodesic balls in hyperbolic space. That's the part, if anything, for you to keep from this lemma. Okay. So with that said, the first theorem, so this is 21. So it's the following. So if I have here, so this is the Maceo-Paccar constant mean curvature foliation, then for h sufficiently close to 1, the region as the interior of sigma h is uniquely isoperimetric, meaning it's a solution of the isoperimetric problem of its respective volume, and moreover, can only be the region for that volume and nothing else. So it's uniquely isoperimetric, and even more is uniquely isoperimetric for both profiles, the standard profile and the outermost profile. It will be an optimal solution for both of those cases. Let's see. Maybe I won't discuss the whole proof, but maybe I will give you, what I think are two of the main highlights, which are, so let me say, quotation proof. So what I would really like is I will just take some isoperimetric region, some sequence of isoperimetric regions with volume increasing, and want to show that they eventually have to enter this foliated area, and then the foliation will force them to be what I want them to be. So for that, I will first assume that maybe I have a sequence of regions intersecting a fixed compact set. So this intersection is not empty for a sequence of volumes going to infinity. So if such thing happens, if I have part of my profile hanging around at maybe not leaving my compact set where I have my foliation, then what I can do is you can use stability to take a subsequence that converges to a surface. So this will converge graphically, smoothly with multiplicity 1. This will be a constant mean curvature surface. It will be stable, meaning that the second derivative of area has to be non-negative. And now from here, there's already work in the 80s, or applying work in the 80s from Fischl, Corbry, and Da Silveira. We can basically reduce the case that this limit object you obtain has to be an orosphere. So whatever these things are, it will be just some orosphere inside of M. And because we're taking limits of embedded regions, then this orosphere will have to be embedded, meaning it will have to appear as I'm drawing it in here. So now a consequence of that is because, well, this is the boundary of my surfaces. The boundary of my surfaces are converging to this. Orospheres, these are, they are strictly convex. Both of the principal curvatures are actually 1. So this will imply that for large I, this region will be locally convex. And from local convexity, what we can do is we can lift the full region sigma vi to H3. And the reason for that is you are not going to have topology appearing at the boundary of your surface. And now once you manage to lift this region to H3, then you remember, wait a second, for H3, I know that things are optimized at geodesic balls, but I already told you because of the lemma, we already knew how to outperform them. So this gives you a contradiction because of the lemma. Actually, in the outermost case, this is a little bit easier because in that case, you already know you cannot live because the outermost profile, you are always containing something that carries topology with you. You cannot just live to H3. So these are the main ideas for the proof. So one nice consequence of this is the following. Now that we know for large volumes who the region is, so we'll just write as a color area and not worry much of the proof, but basically all that I'm saying here is for very large volumes, we know what the profile is. So the Hawking mass is negative unless M is equal to a model with totally geodesic convex core. Again, just the reason for this is for these cases, we know which surfaces are going to be the one that realize it, and we can just compute what the Hawking mass will be. Again, this is a nice criteria to, let's say, it's a nice criteria with a sign to distinguish the particular model metric that comes from this. Okay, so now, so this is being okay, because in one hand, we have renormalized volume that uses some surfaces, and I could use R as large as I want. I could perturb it a little bit, and now I know they become isoperimetric. Now I just want, so we write it here as a proposition, I just want a formula that grades renormalized volume in terms of the profile as a function. So in the formula of renormalized volume, I have two factors that are neither volume or area. They are just the mean curvature and just a factor, the factor of distance. So let me tell you what is the formula. If I have this plus pi over 2 all the characteristics of the boundary, this is the same as limit as r goes to infinity of the volume of omega r minus a half the area of the boundary and the following logarithm function of the area. So this is log of root 2 times the area of the boundary at distance r divided by pi all the characteristic. And now I really need a limit. It's not just evaluation for a value of r. And again, I won't do the computations of the proof other than telling you how do you prove this. The two things you have to prove is that the limit in r of the integral of the mean curvature minus 1, this is a constant that depends on the mean curvature, and also limit of r of the parameter r minus that log term. This is root of 2 times the area of the boundary divided by pi all the characteristic. This limit is 0. Okay, and again, this is what you need, because renormalized volume uses volume, mean curvature, and r, and these two equalities, I'm just telling you how to replace them for something that now appears in this way. Okay. And now, what I'm just going to do is, remembering thanks to Massey-Picard, I know that if I perturb these surfaces a little bit, and by a little bit I mean in such a way that this limit doesn't change, now this becomes the isoperimetric surfaces, and this becomes the isoperimetric region. So I will have the same proposition. I won't write it twice, where here I get to write volume V. Area, that's just the evaluation of the profile. And here again, this area is also the evaluation of the profile. So yes, so really, or maybe one way to geometrically reinterpret renormalized volume using this proposition, for instance, in the case that the manifold is function, is really telling us something about the asymptotics of the isoperimetric profile for a function manifold. Okay. So now, consequences of this and the comparison theorems we have of renormalized volume. So this is again in the same paper. Let me be careful here. So the limit as v goes to infinity of the profile of the model at v minus the profile of m at v, this is always greater than or equal than 0. For the outermost profile, you have always this inequality. Or here, I'm evaluating the outermost profile at V. Here, I'm evaluating it at a translation that is taking the difference between the volume of the outermost region for M and the volume of the outermost region for the model. And you have these inequalities. And if you get any equality, then M has to be exactly the profile. So we have this comparison profile for M in this sense, and both of these comparisons are rigid, meaning they recognize if you are the model metric or not. Yes? Not at the moment. What we were secretly really trying was to reframe renormalized volume as an isoperimetric problem, and then use isoperimetric techniques to prove that. So yeah, we were trying what you were asking, and we sort of like ended at a weird medium where we need both technologies in order to have these results. But that's certainly something very interesting, and maybe we'll highlight there's a lot of different types of flows that people use to study these profiles. But they're classically used, again, in either positive curvature or positive Euler characteristic, which makes it a little bit tricky because you know you have to use a different inequality. If not, at some point, you sort of like, you end with a not useful inequality for what you want to prove. But yeah, thanks. So let me try to tell you 2 words about the proof. So we've got it here. Again, I'm not really doing proofs, but telling you the basic ideas is, now, if I take 2 different manifolds, let's say M and the model metric, I could take the difference of this limit. All the constants cancel. The volumes cancel if I evaluate them at the same volume. So I'm left with the difference of areas. And I'm also left with something that is logarithmic on that, so I will just ignore it for very large volumes. So the very first step is to realize that renormalized volume, that the difference between renormalized volumes is really giving you 1/2 the limit of the profile for the totally geodesic metric and the profile for M. So really renormalized volume in a way is comparing how profiles grow at large scale, which thankfully maybe is a good way to justify that we were really trying to compute infinite volume, and this is sort of like a way to say that we're sort of like succeeding. And for the theorem from Martin, Jeff, and Ken, for the one I also work on, we know that this is less than or equal than 0. So that's the first inequality, and we know what happens with equality, so that's all nice and happy. What happens for the outermost profile? The outermost profile, that's a stronger claim, because I'm claiming something now for all volumes, not just for very large volumes. So really what happens is that is the following. So now here, this is volume, and now this is the profiles. So on one hand, I have the profile of the totally geodesic of the model metric. So I know this one ends higher because of what I just mentioned, and here I will say is more or less the same for the outermost. So I know I'm going to end higher than anything else. I also start higher than anything else, because when you start for the outermost profile for the geodesic model, you have a totally geodesic surface. Totally geodesic surfaces have the biggest area out of any minimal surface in hyperbolic geometry. So it doesn't matter where my model is starting, it's already winning against the profile of my metric M. So I know the profile of my metric M does this. Is below at the beginning, is below at the end. So what is the worst thing that can happen? The worst thing that can happen is this, right? That maybe chooses to go a bit above in the middle, and that's the case we have to discard. And now, if that happens, that means that the difference function has a positive maximum. And now the key part is that this difference function, this can be written in terms of the Hawking mass, which I know it was negative. So you use the negativity of the Hawking mass we prove. I'm assuming that I'm not at the model metric to show like this alleged positive maximum cannot be, because it has the ground sign with the Hawking mass. Again, I'm not really telling you the proof, but I hope at least I'm convincing you that really what you keep in mind is that I get to say that the negative number is not positive. That's really what you aim with this type of inequality. And at least that I know how to claim. Let me say here, just to try to expedite here, because I know we have lunch coming up soon. So let me add here is this chalk more or less visible? I hope so. Here there is the little part where I'm not comparing the profiles at the same volumes. I had to do this translation because I was choosing not to count the volume of the outermost region. So I have to do that choice. Now, if I want, so we can prove this version, which is the one that we sort of like started proving, and is the one from where we were trying to recover all the previous work in renormalized volume, is that we can only prove this using the same methods if the renormalized volume of M needs to be at least as big as the volume of the outermost region. Maybe, and some comments of this, and maybe something I should have highlighted here, is that this quantity by work of Agel, Sturm, and Thurston, this is always non-negative. For the model metric in M, the outermost region and the region you use for renormalized volume and the convex core, everything is just the same. They are the same region. So in that case, everything coincides. Here we have a conditional result. In all cases we know that this is true. So we don't know how to prove this in general, but we know like in every single case where we can say something about which one is bigger, we know that this one is bigger. And by the way, this in particular is a stronger result than the one I was citing from Bridgman, Brock, and Bromberg, and from myself. But that's still open. Okay. So this was sort of like a nice victory for renormalized volume because allowed you to do these isoperimetric comparisons. And then we did this work, and then at some point Agel asked us, could you use these comparisons you did to know where the Cheeger constant is getting maximized? At the point when he asked that, I thought like, wait a second, isn't that known just because Cheeger constant and first eigenvalue of the Laplacian, they're more or less comparable, and we know quite a bit about that eigenvalue. So at that point we were expecting the answer was yes, but it turned out to be no. So let me tell you a little bit what it is. So the Cheeger constant of a manifold, this is just the infimum of the area of the boundary of a region divided by the volume. And again, here I had to define it in this way because I'm dealing with infinite volume manifolds. So just a little caveat like that. There is work of Cheeger that says this is the Cheeger inequality between the Cheeger constants. Sorry, shouldn't forget. Well, I already got Cheeger. This is the Cheeger constant of a manifold. Cheeger around 60s shows that this is bounded above by, in this case, this is the first L2 eigenvalue of the Laplacian. Buser a little bit later in the 80s shows that if I assume that the Ricci curvature of my manifold has to be at least the Ricci curvature of hyperbolic space, then you have a bound from below. Oops. So this in particular will tell me that within these conditions, if I know that my first eigenvalue is very small, I know that my Cheeger constant is very small and vice versa. So a lot of these problems on either spectral gaps or gaps for the Cheeger constant tend to be equivalent while working in this setup. And the reason what I was mentioning is because, again, I'm not quite sure what is the earliest proof of that, but I will just say this follows from work of Bowen and work of Sullivan, which is in the conditions I've been writing things. So with incompressible boundary, the first eigenvalue less than 1 unless M is function. In the case where, in that case, then the first eigenvalue will be equal to 1. So that was the part where we're thinking that, oh, we were sort of like expecting, oh, maybe already people knew about that, or like the equivalent version for the Cheeger constant, but there are some versions that are a little bit similar that maybe I want, just for time. I won't grade it, but it's some work of Montagneux, of one, of Levi Gromov. But let me maybe tell you our results. So this was the sequel that says the following. Again, I need to assume that n is a cylindrical or quasi-function, so all the previous paper applies. Then the Cheeger constant of m is less than or equal than 2 over alpha, where alpha is the only positive solution to alpha equal hyperbolic cotangent of alpha. And this number is more or less 1.66711. Less than 2, less than the Cheeger constant for hyperbolic space. And moreover, equality if and only if m is function. And here, it really doesn't matter the genus. All function manifolds, they all have the same exact Cheeger constant, irregardless of genus. So that's the main result, and maybe, okay, I'll promise I will restrict myself maybe to this part to tell you that an important proposition is here we have a lot of tools for comparable profiles, but we really have to be, at least for one side, I really have to be at the outermost side. Right? I really have to really contain the outermost region for this result to kick in. So if I'm hoping to prove such a result, we will really need to say what the Cheeger constant of a function manifold is, and moreover, that is really realized by something that contains the outermost region, meaning something that contains the totally geodesic surface at the center. So I will just write it as like m function is exactly 2 alpha, and is realized by, so in the product metric I gave you at the very beginning, is realized by the region that goes between minus alpha and alpha. And maybe I will quickly, again, just to keep the style of like I'm just giving you hints of the proof, the part that it was very useful, and we weren't sure if that's this, I mean, if you would ask me, I would say this must surely have been observed before, but we couldn't find a reference. So if you find one, please tell me. The important part is the following. Remember that the metric in the function manifold is given like this in terms of its equidistant foliation. In this case, the gradient the Laplacian of R, hyperbolic tangent of R, is identically 2, which is something, again, like I didn't know it, but it was something very useful. Because remember, we want to say something about the Cheeger constant of a function manifold. So I need to say something about the volume of region versus area, right? I need to say something. Well, volume is just integrating the function 1, or integrating the function 2 and then divided by half. So this is just what volume gives you. But now that you grade it as a Laplacian, you could do integration by parts, and now you have it as an integral of the boundary. And most importantly, the level sets of this function happens to be the level sets of the foliation. And this is the slices of the foliation that minimize the area per volume region. So those are more or less the ideas of the proof and what allow us to say that. So I'll finish just by saying that even though we were like very happy to have this result, something that is now interesting is that for either the first eigenvalue of the Laplacian or for the Cheeger constant, one would like to say which structure maximizes it, not when you test all possible manifolds of this type, but rather when you fix a topological type and you do the competition only within those ones. As far as we know, there's not much know even, the candidate will be the model metric, but it's not much knowing in order to fully finish this question. So okay, I'll finish there so we can go for lunch.